Today we're looking at the December 2025 Jane Street puzzle, where it is a game of robot javelin, and they explain it here. It's a head-to-head battle between two robots who make their first throw, and the distance of their throw is a real number drawn uniformly from 0 to 1. Then, without knowledge of the other robots' draw, each robot can independently decide whether to keep their current distance drawn or erase it and go for a second throw. And if they do throw that second time, they must keep it, and it is also drawn uniformly from 0 to 1. And in the end, the robot with the largest final distance wins. And so we have two competitors here, Javelin and Spears, and they've been competing for a while, so they have settled into a Nash equilibrium for the game. But now we learn that Spears has found an exploit where it can receive a single bit of information telling them whether Java's first throw was above or below some threshold D of their choosing, right, before they want to throw for a second time. And we assume that Spears has a chosen D to maximize their chance of winning. But now, Spears' robot isn't aware that we've actually learned this fact, right? So Spears' robot is still assuming that Java is using the Nash equilibrium strategy, whereas instead Java knows about the extra information that Spears receives. And now if we were to adjust Java's strategy based on this to maximize Java's odds of winning, we want to find, what is Java's updated probability of winning at the end. And we want to give our answer in exact terms or as a decimal rounded to 10 places. So let me copy this puzzle real quick. So what is sort of our plan to solve this problem, right? There's sort of three different steps to solving this. The first one is when they both play fairly, right, and they settle into a Nash equilibrium. Right, this will be part one. We find this Nash equilibrium. Then once we know this Nash equilibrium, we want to find the second part is um, finding this threshold D that Spears decides to choose to better its odds. And then the last part is now assuming Java knows this, and we have to adjust Javelin's strategy to maximize its odds of winning. So that's our third part, to adjust Java's strategy. And so part by part, how do we do this? Well, the idea behind a lot of these strategy games is the Nash equilibrium strategy is something called a threshold strategy, where both players will re-roll or redraw if their first draw is less than some threshold T, and they will keep if their first draw is greater than that same threshold T. And the idea behind this threshold strategy is, say we're Java and we're playing Spears, right? We fix Spears' strategy to be any strategy. Then it has some associated distribution with, its final distance that it throws. Then say we roll some number x. I guess I'll say x is Java, y is Spear. And so we roll some number x, then we have the choice to either keep or re-roll. and both of those choices has some associated probability with it in terms of us winning, Java winning, right? Then surely one of those two probabilities has to be higher than the other. And so if, re-rolling was better, we have a higher probability of winning if we re-roll, then surely we want to re-roll everything less than x, right? So drawing this out, sort of, if we roll some x here, if we decide to if re-rolling gives us the higher probability of winning, then surely we want to re-roll everything below x as well, right? Because it is a lower number. And similarly, if keeping gives us the better odds of winning, then surely we want to keep everything greater than x as well. Because if we're going to keep a lower number, x, then we surely have to keep anything greater than x as well. And so both of those combines gives us this threshold strategy of, you know, at a t, or given this threshold t, we reroll everything less than t and keep everything greater than t. And this threshold strategy also has the nice property that we're going to make use of a lot, is that if we do decide to roll, or if we roll exactly t, then the probability of us winning if we re-roll should equal the probability of us winning if we keep. And this idea of, having the probabilities equal is called indifference. And I guess the intuition behind that is, let's say we have some threshold t that we've decided on. Then if keeping yields a better probability of winning than re-rolling, then this sort of implies we can lower t by a little bit, and the probability of keeping will still be greater than the probability of re-rolling. So this really isn't the optimal t. And on the other hand, if re-rolling is optimal, if re-rolling has a slight edge over keeping, then surely we can increase t by a little bit as well to re-roll a little bit of higher values, and that probability would be greater. That probability of winning if we re-roll will be greater than the probability of winning if we keep. And so again, this isn't the optimal t. So at this t, we have the probability of indifference, and we can use it to find, this optimal t. And so we have to condition on the fact that x, we roll a t, right? X is equal to t. Then if we decide to keep, our probability of winning is equal to the probability that y is less than t. Or I guess I should also mention, right, this threshold strategy, it works for x, but by symmetry, y or spear also has the same logic, right? So in fact, both robots use the exact same threshold t strategy. And so now we can, easily solve for the probability of winning. And winning means in terms of Java winning. Right, so probability of Java winning is equal to the probability, I guess we break it up into cases, or the probability of that y is less than t, so y has to re-roll. And then, or the case when y is greater than t, so y doesn't re-roll and just keeps. Right, and so because it is a uniform distribution from 0 to 1, this happens with probability t, and we need the probability of re-rolling So if y rerolls, the probability that y is less than t because x is equal to t is also just t, right? And then in this case, note that the probability of winning if y is greater than t means that spear won't reroll, spear will keep. So if y is greater than t, then we can't ever win. So this probability is just 0. So this is t squared, and then reroll, or the probability of winning if we reroll, again, we break it up into cases. The case where y is less than t, and then the probability of winning, given that y is less than t, plus the probability that y is greater than t, times the probability of winning if y is greater than t. So again, this is t, and then if y is less than t, then we both Java and Spear reroll to get a second draw, and because they're both drawing uniformly from 0 to 1, by symmetry, Java wins with 1/2, or half of the time. And the probability that y is greater than t is just 1 minus t, and the probability of us winning, given that y is greater than t, we can use this as, given that y is greater than t, Spear will keep, right? So we can view Spear's number now as just some uniform distribution from t to 1. And so if we reroll, we can see that the average value that Spear will get is in the middle here, right? 1 plus t over 2. Then because we are drawing from a uniform distribution, and the average value that Spear will have is 1 plus t over 2, our probability of winning is our probability that our number is greater than this average value. And so that has a probability of 1 minus 1 plus t over 2, or just the length of this part. And so this comes out to be 1, or t over 2 plus 1 minus 2t plus t squared over 2, which is just t squared minus t plus 1 over 2. And now we can use our indifference principle and set these two quantities equal. So we have t squared is equal to t squared minus t plus 1 over 2. And so solving for t, we have that t squared plus t minus 1 is equal to 0. And so I guess you can use the quadratic formula to find that t is equal to -1 plus or minus the square root of b squared plus 4 over 2. So -1 plus or minus square root of 5 over 2. And which one do we take? Which solution do we take? Well, if it's a minus, then this entire expression is negative, which doesn't make sense. So we actually just have that t is equal to root 5 minus 1 over 2. And that's our threshold value for this first part. And just for some intuition, it's around 0.618. So for this first part, we have that both Java and Spear will reroll if their first draw is less than t, root 5 minus 1 over 2, and they will keep if their first roll is greater than square root of 5 minus 1 over 2. And that's the first part. So now for the second part, we have to determine the optimal D that Spear will choose for receiving a single bit of information telling them whether Java's first throw was above or below D. And intuitively, it makes sense to just set D is equal to T, right? Because I guess if we look at this number line a little bit, for a little bit, we have T's somewhere here, right? If we set D is equal to T, then what this does is it'll let Spear know exactly when Java rerolls and when Java keeps, right? Because if Spear receives that um, Java's throw was less than D, then via our threshold strategy from part one, we know that, or Spear will know that Java rerolled. Where if D receives that, or if Spear receives that Java's first throw was greater than T, then Spears knows that Java kept. On the other hand, if we set D to some other value, let's say we set D to somewhere less than T, then if Spear receives that Java's first throw was less than D, then I guess Spear will also know that Java decided to reroll. But if Spear receives that Java's throw was greater than D, somewhere here, Spear won't be able to deduce any information about what Java did, right? Because Java might have rerolled if its first value was between D and T, or Java might have kept if its first row was between T and 1. And so we lose all of this information that we would have otherwise gotten. And similarly, if D was greater than T, then we know what happens if Java's roll was greater than D, right? Java would keep. But if Java threw something less than D, again, we lose all of this information. We won't get any new information about that. And surely that can't be optimal. So in fact, we set D is equal to T. And so this sort of implies Spear knows 100% if Java re-rolled or not. So that is the second part. For the third part, or the last part, we have that Java now learns that Spear Robot has this extra bit of information. And so now we have to adjust Java's strategy based on this. And so the first thing we want to do is actually, given that D is equal to T, we want to determine what is Spear's strategy, given that Spear has this extra bit of information. So let's say like 3.1, Spear's strategy. And so again, there should be two cases that we want to consider, right? If Spear receives that Java rolled less than T, or less than D, which is equal to T. So if Java rolled, so if Java re-rolled, and that is when X is less than D, then from Spear's view, Java's new number, let's say X prime, is uniform between 0, 1. And if Java's number is going to be uniform from 0 to 1, then this implies that Spirit should reroll if its first roll is less than 1/2, right? Because on average, Java's number is going to be 1/2. So if Spear's number is somewhere less than here, on average, Spear is going to, or if Spear rerolls, on average, he'll get a bigger number. You can think of it that way. If Spear's first roll is less than 1/2, then if he rerolls, Spear's new number will be on average greater, right? And that's optimal. Whereas if Spear's number is greater than 1/2, on average, if Spear decides to reroll, then on average he'll get a lower value. And that's worse. On the other hand, if Spear receives that Java kept, so x is greater than d, then from Spear's point of view, Java's number, right, or its first roll is actually now uniform because we're conditioning that x is greater than d. Then x is now just uniform from d to 1. And by a similar logic from part 1, we have that Spear rerolls again for some threshold if y is less than c for a threshold c. And I guess in the first case, it's also a threshold of 1/2, but you can sort of reason that out intuitively instead of needing to do any calculation. But the second part is a little bit more tricky. So we have the Spear rerolls for another threshold, and so you want to find this threshold, right? And we again use the idea of indifference at this threshold. So we condition on y is equal to c. Then if we keep, then I guess now we're in Spear's POV. And the probability of Spear winning is equal to we actually need to do something else real quick. So right now we're looking at this region, right? When x is greater than d is equal to t. So ideally we actually want c to be in this range as well, right? Because if c was outside, like before this range, somewhere out here, then keeping any of these values doesn't really make sense because Java's value is always going to be greater than it. So we have that c is somewhere between t and 1. And so now we can condition on y is equaling c in that range. And the probability of us winning is, if we decide to keep, we need Java's value, or Java's first roll, to be somewhere in this range, right? And so that has length c minus t. And I guess because we're also conditioning on the fact that Java's value is going to be in this range, right, from t to 1, then Java's value is going to be uniform from t to 1. So we have to divide by the length of the range. So 1 minus t. And then the probability if we reroll, or the probability of winning if we reroll, is, right, we can use the same idea. On average, Java's value is going to be 1 plus t over 2. So when we reroll, our uniform, and when we reroll, Spear's number is going to be uniform from 0 to 1. And so we need it to be greater than this, greater than the average value of Java's roll. And so this probability is again 1 minus 1 plus t over 2. And we don't divide by 1 minus t this time because Spear's reroll, we're looking at Spear's reroll, which is uniform from 0 to 1. I guess technically we are dividing by 1, but I just haven't been writing it. So now again, we can set these two equal by the indifference principle, or indifference property. I'll just write this as 1 minus t over 2. And so solving for c, we have that c is equal to 1 minus t squared over 2 plus d t, and this is just equal to t squared plus 1 over 2. And so just plugging in our value of t from up here, we get that c is equal to 5 minus root 5 over 4. And so this is about 0.691, which matches our intuition that c is between t and 1, right? Because t is 0.618, so c is a little greater than t. And so what does, I guess, our situation look like now? It is that, or I'll draw the number line again. From 0 to 1. For reference, this is 1/2. We have that t is somewhere, t is 0.618. So it's somewhere, let's say here. And then c will be somewhere here. I'll write t is equal to d. So we have that if Java rolls between 0 and t, then if Spear's first roll is between 0 and 1/2, then they will both re-roll. And then if Spear's first roll is between 1/2 and 1, then Java will re-roll, but Spear will keep. In the other cases, if Java's first roll is between t and 1, then Java will keep. But if Spear's first roll is between 0 and c, then Spear will re-roll. But if Spear's first roll is between c and 1, then Spear will keep. And so that is our current situation now. And so now, right, 3.1 was we figured out Spear's strategy, and now I guess 3.2, we have to adjust Java's strategy. And again, we need to break this up into cases. Um, and in particular, that is if Java's first roll is less than t is equal to d, right? Because Spear's strategy changes depending on if Java's roll is less than d or greater than d, we should divide it up based on that case. So if Java's first roll is less than t, then we have that Spear rerolls if its first roll is less than 1/2. And so again, we can use the threshold and indifference principle to reason that there should be some value a for where Java will reroll if its first roll is less than a, and will keep if its first roll is greater than a. And we want to reason that a is actually between 1/2 and t, right, somewhere here, because if um if this threshold a is less than 1/2, then because Spear rolls or rerolls if its first roll is less than 1/2, then, you know, on average, his roll will be greater than any a here, right? So the fact that we have to keep all of these numbers will, on average, be detrimental to us because Spear is keeping anything up here and re-rolling everything down here. So we want that a is actually greater than 1/2, and the idea behind it being a little bit, not exactly 1/2, but a little greater than 1/2 is because Spear's, I guess, average is a little greater than 1/2, right? Because he's going to re-roll everything down here. So we want to be a little bit more aggressive and re-roll stuff greater than 1/2 to sort of compensate for that higher average that Spear has. So again, we want to condition that x is equal to a, and again use our indifference. So if we decide to re-roll, then I guess now we're in Java's POV. The probability of winning is, we want to break it up into two cases again, based on what Spear's roll is, right? The case when Spear's roll is less than 1/2, plus the probability that Spear's roll is greater than 1/2, and so we condition on that. And again, we're conditioning on x is equal to a. Then this first case, this happens with probability 1/2, and then the probability that we win, given that it is 1/2 is or in this case, both Java and Spear are rerolling. So again, by symmetry, we have that the probability of winning is 1/2, and then in this case, also 1/2. And then the probability of winning, given that y is greater than 1/2. Given that y is in this range, right? On average, it will be 3/4. So because we are assuming that Java rerolls, then we need the reroll to be greater than the average value of y. So that happens with probability 1/4. And so in this case, the probability of winning is 3/8. And then we want, what if we keep? Again, we have to condition on this. Or the probability of winning is equal to this, which again, this will be 1/2. And then the probability that we win, given that y is less than 1/2. So we're at A, or I'll redraw it, I guess. The case we're at right now is right, given that y is here, Spear will reroll. Right? So we're at A and we're keeping. So if Spear rerolls, the probability of the reroll being greater than A is just 1 minus A. And then in the second case, this is 1/2. And the probability of winning, given that y is greater than 1/2, is, right, given that y is greater than 1/2, we're conditioning on y being in this range. So y is uniform from 1/2 to 1. And so the probability that it is greater than A is just we want the probability that, oh, I messed this part up. This is in Java's point of view right now. So the probability that Java wins is if, so this first part, let me redo this first part. If y is less than 1/2, Spear rerolls. So the probability that it is less than, the reroll is less than A is the length of this. The length of A over the entire length. So this is A actually. And then in the second case, we have that y is in this range, and the probability that A is greater than y happens if y is between 1/2 and A. Right, and this happens with probability A minus 1/2 over the length of what we're conditioning on. So 1/2. And so solving, we have that this is equal to 3A over 2 minus 1/2. And so, again, equating because of indifference, you have that 3/8 is equal to 3a over 2 minus 1/2. So a is equal to 7 over 12, I think. Yeah. So in this case, right, if Java's first roll is less than t, then Java rerolls if x is less than a, right? And keeps if x is greater than a. And I guess again, this value of a matches our intuition that a is between 1/2 and t. And now for our last case, where this case was when x is less than d, when x is less than t equal to d. And so case 2, we have to use condition on x being greater than t equal to d. And again, we do something similar. If we decide to re-roll, or sorry, first, again, it should be a threshold strategy for Java. We want to keep for anything greater than some threshold. Let's say at your threshold A. We have threshold, let's say B now. And where's B in our graph? We want B, I guess, somewhere to be in here. But as we want to be a little careful, or in this case, where are we? We're conditioning on x is greater than t. Spear's strategy will be to re-roll everything less than c, right? And in particular, Spear is re-rolling all of the big numbers in this range, right? Which surely can't be too good for it, because if you're re-rolling that, on average, you're going to get 1/2, which is going to be less. And similarly, for Java strategy, we don't, if we're already in this range, do we really want to re-roll only to get, a worse value on average? And so, we might hopefully guess that maybe we want to keep everything in this range. And we can quickly check that by just looking at this endpoint value, setting x is equal to t, and finding the probability of winning if we keep versus reroll. And if the probability of keeping is higher, if the probability of winning if we keep is higher, then surely by, what I explained in the beginning, we want to keep everything greater than t as well. So let's quickly check that. So get rid of this threshold. We want to look at the probability conditioning on x is equal to t. Then if we re-roll, the probability of winning, again still in Java's POV, is, again, two cases. I won't write it out this time. if C, or if Spear's first roll is less than C, then Spear will reroll. So this happens with probability C. And if Spear rerolls, then both Java and Spear are rerolling. So they win. Java wins with probability of 1/2 by symmetry. And in the case where Spear's roll is greater than C, I guess I'll draw it out for this one. Right, the first case, if Spear's first roll is in this range, they're both rerolling, so 1/2 chance of winning. If C's roll is in, or if Spear's roll is in this range from C to 1, happens with probability 1 minus C. I guess recall that T is somewhere between here, right? T somewhere here. So the probability that Java wins is Java is re-rolling, and Spear's value is somewhere in this range where he's keeping. So on average, it'll be here, which is 1 plus C over 2. So Java's reroll needs to be greater than the average, so this range. Right, and this happens. Java's reroll will land in this range with probability just this length. So 1 minus 1 plus C over 2. So again, this equals C over 2 plus 1 minus C squared over 2, which will equal C squared minus C plus 1 over 2. So plugging in the value of C we found from before up here, you'll get that this is equal to 13 minus 3 root 5 over 16, which is about 0.3932. So if Java rerolls, it has a probability of winning of around 0.4. On the other hand, if we keep, then the probability of winning is we're keeping at x is equal to t, and so again we condition on Spear's roll. If Spear's roll is less than C, then Spear is rerolling. So this happens with probability C, and rerolling to something less than T is just probability T. And then the other case where Spear's roll is greater than C, so in this range, well, Spear's keeping that, and any value in this range is greater than T. So Java wins with probability 0. So plugging in the value of C and T that we found, we got this is around 3 root 5 minus 5 over 4, which is around 0.427. So indeed we have that, the probability of winning given we keep is greater than the probability of winning if we reroll. So if at t, right, if at t Java prefers to keep, then surely anything greater than t, Java will also want to keep. And so Java is keeping all values in this case, right? And so combining, right, this case 1 and case 2, or I guess in this case, Java always keeps. So combining these two, we have that Java's updated strategy is just reroll if x less than a, and keep if x is greater than a. And so now that we have that, we just need to calculate, I guess, our step 4, Javelin's updated probability of winning. And I guess let me copy this picture down. And so probability of Java winning is equal to, and to calculate this probability, there are, I think, 4 cases we have to break it up into. The first case is if x is in the range how do I do this? I'd rather like this. X is in 0 to a, right? Because in this case, I'll just write all 4 cases for now. Or first. So, and we have to split it up because each case has a different, Java and Spear both have different strategies, right? So in the case where x is between 0 and a, we have that Java will reroll, right, based on this. X is less than a. So Java will reroll, and Spear will also reroll, right, based on this strategy. And we calculated before that, or I guess the probability that x is in this range is just a, right? And then we calculated in this case that somewhere up here, in the case where x is less than t, which we have right now, we're re-rolling, so our probability of winning is 3/8. So the probability that Java wins is 3/8. In this case where x is in a and t, x is between a and t, Java will keep, and then Spear rerolls if y is less than 1/2 from here, right? Because I guess Spear thinks that x is less than d. We have that between a and t, or a and d. Spear thinks that Java is going to reroll, so Spear will reroll if y is less than 1/2. And so what's the probability of Java winning given this situation? If Spear's first roll is less than 1/2, which happens with probability 1/2, then we need Spear's reroll to be less than the average value of Java's here. So this happens with probability a plus t over 2. Or if Spear keeps, or Spear's number is greater than 1/2, then we have Java's number is in here. If Spear's number is in this range, then Spear keeps it and Java will always win. So we get a probability of that range over what we're conditioning on, which is this half of Spear's roll, plus if Spear's roll is in, if both of their rolls are, Java's roll is still in this range, if Spear's roll is also in this range, then this just happens with both of them win with probability 1/2 by symmetry. So the probability that Spear's roll is in that range is t minus a over 2, which is the length of it, or sorry, the length is t minus a, and then we divide by what we're conditioning on, and then times a 1/2 for Java winning with probability of 1/2 if both of their numbers are in this range. And then if Spear's number is in this range, then it'll always be greater than Java's number in this range. So Java can never win. So that's that case. If Java's number is in the range from t to c, which happens with probability c minus t, then what happens in this case? X is greater than a, right? So Java will keep, and Spear will re-roll if, right, so Spear thinks that Java kept, so Spear will re-roll if y is less than c. I guess this will all be the same. So in this case, Spear re-rolls if y is less than c. And so if y is less than c, or so that happens with probability c, then that's x. We need Spear's reroll to be less than the average value of x. Right? We need Spear's reroll to be in this range. And this happens with probability c plus t over 2. And I guess if Spear's roll is in this range, then it'll always be greater than Java's kept value. And Spear is keeping everything in here as well. So Java can't win. That's this case. And for the last case, between C and 1, yeah, again, Spear rerolls if y is less than c. So if Spear does reroll, then it needs to be less than the average value of x, which is c plus 1 over 2. Or if if Spear keeps its value in here, then both Spear and Java's value is in between c and 1. So by symmetry, Java wins half of the time. And so this is the expression for, Java winning And if you plug in all of our values for A, T, and C that we found, we get that it will be equal to 229 minus 60 root 5 over 192, which is around to 10 decimal places 0.49399370904, which is our answer. And that solves December's Jane Street puzzle. But the main idea is just using the idea of thresholds, um, that you're indifferent at the threshold point and just looking at a bunch of cases. And that's it.